When we look at stars, they are so much further away than our sun that we can't see the kind of detail that we did with our sun. So we're going to stick to the properties that are easier to see. We're going to study a star's luminosity, the surface temperature, and the mass. Mass is called the fundamental property because if you know the mass of a star, you know what the surface temperature is supposed to be, what the luminosity is supposed to be. The mass of the star determines the other properties. A single star might live for 100 billion years. So we can't watch one single star form, burn through its fuel, and run out of fuel and explode. We've got billions of stars to work with. So what we can do is just basically a population survey of the universe, and we try to figure out how long does it take for a star to form? How long can its fuel last? How does a star die? And we piece it together star by star by star. So let's start off with some definitions. Luminosity. Luminosity is the total power a star emits, and you might measure that in watts. And that depends on the star's surface temperature and the size of the star. Recall back to the chapter we did with spectra and thermal radiation. And thermal radiation had two laws. Right? The amount of power coming off of a star depends on its surface temperature, because that affects the thermal radiation spectra, the rainbow, and also the size, because a bigger star will have more surface area, and so you'll have more total power coming from it. Apparent brightness is how bright a star looks to us on Earth. Right? So the further away something is from you, the dimmer it will look. And so we measure that in magnitudes, which is a historical unit, so it's a little bit backwards. We'll get to that in a second. And how bright it appears to us on Earth depends on the temperature and the size, just like the luminosity did, but now also the distance. So instead of saying temperature and size here, I could have said its luminosity or its wattage. Right, so be careful using the word brightness in this chapter and here on out, because if you say brightness, right, you're not talking about the wattage of the star. You're talking about how bright it appears to you on Earth. So the magnitude system was started by the ancient Greeks, and the brightest stars in the sky were called magnitude 0. And then the next brightest set of stars was called magnitude 1. The dimmest stars that you can see with your human eye are called magnitude 6. Right? Even dimmer, with my telescope I can see stars that are even dimmer. I can see down to a magnitude 10 or 12 with my telescope. So the larger the magnitude, the dimmer the star. So what about the sun, which is something the ancient Greeks didn't think to categorize? The sun is actually magnitude -24. So in this case, a larger magnitude is a dimmer object. So the wattage of a star, the luminosity of a star, is connected to how bright it appears to us just through distance. And so we have an equation for that, and the equation is called the inverse square law for light. And if you like equations, here's the equation. But if you don't like equation, we'll go through the words. Okay. So let's start here. Both of these objects, object 1 and object 2, appear to me right now to have the same brightness. They look the same to me. But without more information, I can't really tell which one is more powerful, which one is giving off more actual power. So if you reveal the objects, if you have a little bit more information, right? If the lighthouse appears as bright to you as a candle does, right? Doesn't that mean that the lighthouse is further away? Because you assume that the lighthouse is giving off more power. So the equation links brightness and luminosity and distance. And so algebra says that if you can find two of these pieces of information, Math will let you solve for the third. And the easiest one for us to find as astronomers is brightness. How bright does it appear to us on Earth? So if you can see it, you can figure out its brightness. So then that leaves these two. And it might depend on the situation. Maybe in one situation, it's easy enough to measure the brightness and you know the distance. If you know the distance, this equation lets you calculate the luminosity. In a different situation, you might be able to measure the brightness, and in this situation, maybe you know the luminosity of that object, the wattage of it. Then you can use it to find a distance. And this last case is actually really important for us. We often use this trick to calculate the distance to something, or at least to estimate the distance to an object. The second property of stars that we can compare is their surface temperature. And remember from chapter 5 that the surface temperature of a star can be estimated from its color. Hotter stars appear bluer, cooler stars appear redder. And from the laws of thermal radiation, we could actually find the surface temperature of a star. And so we should be able to end talking about surface temperature right now. We should have already figured this out. We're good, right? Slight problem. Space is not perfectly empty. There's little bits of gas and dust out in space. And so, let's say there's a yellow star. That light will travel through the dust, and the dust will absorb a little bit of the blue light, making that star look red when it should have looked yellow. So this actually isn't going to be good enough for us. So it turns out that the temperature of a star's atmosphere affects which chemicals, which elements can make spectral lines in your star. So the hottest stars, so here's temperature, the hottest stars allow this spectrum to be created from its atmosphere. As you go to cooler stars, different atoms and different isotopes are allowed to make different spectral lines. Historically, right, these were ordered A, B, C, D, E, F, but eventually we realized that there was a more physical way to sort them and sort them by temperature. So the hottest category of spectra is called type O. The next hottest category of spectra is type B, A, F, G, K, and M. The mnemonic is O, B, fine gal, or you could say guy, kiss me. Hottest to coolest. Oh, be a fine guy, kiss me. Okay. Each one of these is also broken down into 10 subcategories, so it can be O1, O5, O10. We're not going to worry about that. F, F1, F2, F3. We're not going to worry about that. Our sun is a G-type star, for reference. The last property that we would like to know about stars is mass, and actually that's the best one to try to find out because mass determines the other properties. So let me put up here Newton's version of Kepler's third law. It says that the time for one orbit is based on the separation between the objects and the total mass of the two objects. So before we were talking about this of a planet going around a star, or maybe even a moon going around a planet. But if we're going to be looking at things that are really far away, we want to look at bright things so they're easier to see. So we're going to use binary stars. So we're going to watch binary stars, and we're going to watch them orbit and figure out how long it takes for an orbit. Right, and how much separation is between them, and that will tell us the total mass. So we're going to use Newton's version of Kepler's third law to find the total mass of those stars. And then we can figure out how much is in star A and how much is in star B. And then we find the mass of stars and we can start to learn about them. Binary stars are not rare. Binary stars are really common. About half of all stars orbit another star. If that's confusing to you, let me draw a little diagram. A lot of times when I say that, people think that means that all stars should be in a binary system. But here, let's take a sample of 4 stars. There's 4 stars in the universe. Right? About half of all stars orbit another star, so let's make these 2 a binary system. So these 2 are a binary system. And this star does its own thing, and this star does its own thing. So there, half of all stars orbit another star. There are 3 ways that we look at binaries. The first one is called the visual binary. Basically, that means that you can see the stars, and that means that you can watch them orbit each other in the sky. Here's a picture from 1940 of a visual binary. You come back in 1950, you can see that they've moved. Come back in 1960, they moved even further. So if you can figure out how long it takes for one full orbit, and you can figure out their average separation, it would let you determine the total mass of those 2 stars. Another category of binary is called a spectroscopic binary. And in this animation, it shows you one binary star going around another binary star. But maybe we can't actually see them like this in space. We can't actually see the 2 stars going around each other. Maybe all we're able to get is the spectra. Maybe all we're able to see is the spectra of one star down here. And we can actually use this information to figure out the total masses of the stars. The third category of binary is called an eclipsing binary. And we say that this only works for edge-on orbits. So let me introduce edge-on and face-on. So an edge-on orbit would be one star here, and the orbit of the other one, from our point of view, orbits and then comes back, right? So you're viewing it from the side and along the edge of the record. The other way is called face-on, so maybe this is the heavy central star, and you're watching it orbit this way. That's called the face-on orbit. So eclipsing binaries requires this edge-on orbit, so that one star will move in front of the other one from our point of view. So in this animation, you'll see star 1 and star 2, and they'll orbit each other, and star 1 will pass in front of star 2, and then on the other half of the orbit, star 2 will be in front. And so in this case, we can't actually see star 1 and star 2 as separate dots of light in the sky. Right? Remember resolution? They might be blurred together in one total dot of light. But what we could tell is that the dot of light is brighter when both stars have a sight line to us, but when one blocks out the other one, it actually gets dimmer. Okay. And now that we've done this for oodles of stars, we've found out their surface temperature, we've found out their luminosity, and we found out their mass, it turns out that mass is the best one. If we could learn only one piece of information about a star, we would pick mass. Because if you know the mass of it, you know what the luminosity is supposed to be. You know what the color is supposed to be, the surface temperature, the spectral type. the lifetime of the star, the physical size of the star. All of these things are determined by mass. So let's look at some stable stars. The most massive star here is Spica. And because of its mass, it determines how fast it fuses the hydrogen into helium. And that determines its spectral type, which is B, spectral type B. It also determines its physical size, the radius. It would also be the most luminous. This would be the most luminous, most powerful star. And if you change the mass, so let's go to something less massive, it will fuse its hydrogen into helium slower, so it'll be less powerful, it'll be less hot, it'll be type A, it'll have a smaller physical size, it will actually live longer because it's burning its fuel slower. And then you can just continue that further and further. So if I want to know something about a star and I go to a catalog, the first thing I look up is its mass.
Seen from Earth, our sun is a blinding ball of light. But take away the glare, and one of the most powerful objects in the universe appears in our own backyard. It's a ball of superheated gas that's been lighting our solar system for 4.6 billion years and dominates all life on Earth.
The sun is 93 million miles away, and that means in actuality it's immense. You could fit 1 million Earths inside the sun.
It's over 1 million kilometers in diameter, yet our sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our sun. Betelgeuse, 300 times larger than Eta Carinae. If it was our sun, it would reach as far out as Jupiter. And then there's this monster, VY Canis Majoris, the largest star ever discovered, 1 billion times bigger than our sun.
So in that video, you were able to see that our sun is huge compared to the Earth, but some other stars are huge compared to the sun. Okay? Stars form in nebulas, which we'll talk about in the next chapter. And when stars form in nebulas, it's much more likely that the star that you're forming is low mass. So here's a survey of stars. And the high mass stars are really actually rare. For every 200 tiny stars that you form, you might form one massive blue star. So I have this animation that lets me hide certain populations of stars. So let's just do the intermediate mass stars, so stars like our sun. Okay. Those are all the stars that are like our sun. Quite a lot of them in this picture. Okay. What if I just do the high mass stars? Very few of them. So there's very few high mass stars, a lot of intermediate mass stars. And let's go to the tiny little red stars. But shouldn't there be more? There should be more tiny red stars than there are of the intermediate stars. The trick is that the red stars are so dim they're hard to see. They're in that picture, they're just not bright enough to see. Let me also show you the red giants. Red giants are stars that are running out of fuel. So they're not stable. They're not really in this survey. These are only stable stars. The high mass, the intermediate, and the much more numerous but hard to see red stars.